In this lecture, we'll be looking at the introduction to Stack. In this lesson, we are going to introduce you to Stack data structure. Data structures, as you know, are a way to store and organize data in computers. So far in this series, we have talked about arrays and linked lists. Now in this lesson, we are going to talk about stacks, and we're going to talk about stack as abstract data type, or ADT. When we talk about a data structure and abstract data type, we only talk about the features or operations that is available with this data structure. We do not go into the implementation details. So basically, we define the data structure only as a mathematical or logical model. We will have a look at the logical view of stack. Stack as a data structure in computer science is not very different from a stack as a way of organizing objects in the real world. Here are some examples of stack from the real world. First figure is a stack of dinner plates. Second figure is of a mathematical puzzle called the Tower of Hanoi, where we have 3 rods or 3 pegs and multiple discs, and the game is about moving the stack of discs from one peg to another. The constraint is that the larger disc cannot go on top of the smaller disc. The third figure is a pack of tennis balls. Stack is basically a collection with a property that an item in the stack must be inserted or removed from the same end, and we call that the top of the stack. In fact, it is not just a property, but a constraint or restriction. Only the top of the stack is accessible, and any item must be inserted or removed from the top. A stack is also called a last in, first out collection. The most recent item in the stack has to go out first. In the first example, you will always pick up a dinner plate from the top of the stack, and if you have to put the plate back on the stack, you will always put it on the top of the stack. You can argue that I can slip a plate from the side without removing the plates from the top, though the constraint that I should take it out from the top is not strictly enforced. For the sake of argument, this is fine. You can say this. For the other 2 examples, where we have discs and a peg and tennis balls in a package that can only open from one side, there is no way you can take out an item from the side. Any insertion or removal has to happen from the top. Now let's define stack as an abstract data type. A stack is a list with the restrictions that insertion and deletion can be performed only from one end, called the top of stack. Now let's define the interface or operations available with stack ADT. There are 2 fundamental operations available with stack. An insertion is called a push operation, and it can insert or push some item X onto the stack. The second item is called a pop. Pop is removing the most recent item from the stack. Push and pop are the fundamental operations, and there can be a few more. Typically, there is an operation called top that simply returns the element at the top of the stack. And there can be an operation to check whether the stack is empty. So this operation will return true if the stack is empty and false if it is not. So push is inserting an element onto the top of the stack, and pop is removing an element from the top of the stack. We can push or pop only one element at a time. All of these operations I have written here can be performed in constant time, or their time complexity is big O of 1. Remember that the element that is inserted or pushed onto the stack last is popped or removed first. So stack is called last in, first out structure. Logically, a stack can be represented like something like this, as a three-sided figure, as a container open from one side. This is a representation of an empty stack. Let's name the stack S. Let's say that the stack is a representation of a stack of integers. Right now, the stack is empty. I will perform push and pop operations to insert and remove integers from the stack. I will first write down the operation and then show you what will happen in the logical representation. Let's perform a push. I want to push 2 onto the stack. The stack is empty right now, so we cannot perform a pop operation. After the push, the stack will look something like this. There is only one integer in the stack, so, of course, it is on top. Let's push another integer this time. I want to push 10. And now, let's say we want to perform a pop. The integer at the top right now is 10. With a pop, it will be removed from the stack. Let's do a few more push. I just pushed 5 and 7 onto the stack. At this stage, if I perform a top operation, it will return me number 7. Is empty will return me false. So this pretty much is a stack data structure. Now, one obvious question can be, what are the real scenarios where stack helps us? Let's list down some applications of stack. Stack data structure is used for execution of functions in a program. We can also say that stack is used in recursion. Recursion is also a chain of function calls, it's just that all of the calls are to the same function. Another application that uses stack is we can use it to implement undo operation in an editor. Right now, I am pressing Ctrl Z to undo. And you can see the text is being erased. You can implement using this stack. Stack is used in a number of important algorithms like, for example, a computer verifies whether parentheses in a source code are balanced or not using a stack data structure. Each opening curly brace or parenthesis in source code must have a closing parenthesis or curly brace at the appropriate position, and if they are not, the compiler will throw an error. And this check can be performed using a stack. This much is good for an introduction. Until next time, see you.